Yeah, welcome to week 2. So I wanted to start by finishing up the proof from last lecture. So remember I was trying to show you that classical CDS provides an upper bound, or the randomness cost in classical CDS provides an upper bound on the entanglement costs in F routing. And we had gotten partway there, so we'd shown that the randomness cost in CDS was an upper bound to the entanglement cost in what we called CDQS prime. So that was like quantum CDS with a classical secret, but quantum resources. And then that was an upper bound up to a factor of 2 to fully quantum CDS, where the secret is quantum. And then we were trying to relate this to F routing. Okay. And then we had these somewhat complicated looking definitions of quantum CDS and F routing, but they're expressing something pretty simple. So quantum CDS, there's 2 conditions. There's a correctness and security condition. Correctness is saying that when F is 1, right, when the inputs are such that F is 1, that the referee can recover the quantum system Q, right? And the way that we say that is, think about the channel implemented by the joint actions of Alice and Bob, right? That's what we called N. It can depend on X and Y. It maps from quantum system Q into the message system M. And we said that what it means for the referee to recover the secret is that they have some channel that inverts that one, right? So that the overall thing is the identity. Okay. Or it's epsilon close to inverting it. Okay. And then for security, we said that, well, that means that in all 0 instances, there should exist this thing we call the simulator channel, which just prepares a state, right? It's a channel from the empty set into M. And that should have the property that the output of Alice and Bob's operations, like the message system, is close to just tracing out the input Q and preparing that state, right? So in other words, the message just doesn't have anything to do with Q. Okay, it only depends on X, Y. Okay, that's delta security. And then F routing, the thing we're trying to relate this CDQS thing to, looks like this. So, we have Alice and Bob's operations. We have this cross communication. We're going to call everything that goes left M prime. Everything that goes right will be M. And then when F is 0, we should be able to recover Q on the left. And when F is 1, we should be able to recover Q on the right. Okay. And then the way that we express that is similar to the correctness condition there. So we say that we're going to call Alice and Bob's joint operations M. And then this is just saying that when F is 1, I can trace out M prime, the stuff that went left, and recover Q, right? I can invert this channel. And then when F is 0, I can trace out the stuff that goes right and invert this channel and get back Q. Okay. Everyone's happy with the definitions? Yeah. Okay, so then we're going to relate these things. And the technical tool we needed, or that we're going to use to relate these things, is this theorem. It's called the decoupling theorem. Well, a decoupling theorem. There's various things that are called decoupling. And the way that this works is we have this idea of a complementary channel. Oh, sorry, this is to E. So we have a channel from A to B. We think about a dilation of it, and we trace out, we apply the dilated channel, the isometry, and then we trace out B, and that defines a new channel into the environment, right? From A into the environment. And then basically what this is saying is that if the information goes, doesn't go into the environment, then it's preserved in the channel. And if it does go into the environment, then it's lost in the channel. So if the complementary channel, the map into the environment, is close to completely depolarizing, which is just like a state preparation channel, has nothing to do with the input, then there's an inverse, right? This is small. And conversely, if there's an inverse, right, if this D acting on N can be close to the identity, then the complementary channel is close to completely depolarizing. Okay, good. So with this all set up in the right way and laid out next to each other, it may be reasonably clear that these things are connected, but let's just go through it. So the transformation that we're going to make between CDS and F routing looks like this. So let me first of all draw the F routing protocol. Okay, there's some operations here. Let's call it N left, N right. Actually, let's call it V. V left, V right. W left, W right. Okay. Q goes in here. This is just, depends on Y, depends on X. Okay, so that's an F routing protocol. And then to build the CDS protocol, quantum CDS protocol, we're just going to take a trace. So Q goes in. We're going to do the same operations here and here, except now everything that would have gone left, we're just going to throw in the garbage. Okay. And I claim that defines a CDQS protocol. And then, so to go this way, we trace. And to go back, we purify. Okay, so we take the dilation of these channels, and we take the purifying systems, and we send them left. Okay. Okay, so why does that work? Let's first of all deal with. Okay, so let's go this way first. We're going to start with F routing. We're going to get a CDQS. And so we need to show two things. We need to show that this thing is correct and that this thing's secure. And that's going to follow from the two properties of F routing that we have, which are the correctness in 1 instances and correctness in 0 instances. And so, okay, so for correctness, we need to show that there exists a channel D such that this is true, and XY. Right? But what is N in this CDQS protocol? Well, I said it's just, we do the same things as we did here before, and then we trace out M prime, right, this stuff going left. So this is just dxy right, by the way we define this transformation. That's what this channel was. But this was just the one correctness condition in F routing, right? That's exactly what we said could be made small from this top condition. Okay? Okay. So good, we're done there. And then the other thing we need to show is a security statement. So we have to show the existence of this simulator channel. Okay, and we're going to start now with correctness in 0 instances. So, okay, which way do I want to do this? Okay, so the reason he's going to go kind of backwards here. So I'm going to start with the thing I know about F routing, which is that there exists this channel D, and it goes to Q, trace. Okay, so I have this. This is, okay, so now if I look at, what do I want to use? I want to use this second statement here. So this channel, right, this is my n goes from Q to M, or M prime, M prime. So this is n goes Q to M prime, right? And then this channel, right, is just this thing, right? We know this exists by the correctness of the F routing protocol on 0 instances. Okay, so we get that this thing is not larger than epsilon 0. So then that tells me that there exists some completely depolarizing channel so that the complementary thing is close to that completely depolarizing channel, right? So this says, from that second statement, that there exists S, so I'm getting my labels messed up, which maps from nothing to M such that complementary channel to this one, complementary, so that's now a map from Q to M minus that. Okay, so now we know that this is less than 2 square root epsilon naught. Okay. Is that clear? Yeah. Okay, so it's just saying, like, we're just saying, okay, here, the information went to the right, or sorry, actually it went to the left. We're dealing with correctness in 0 instances, right? Q went to the left. And then reviewing, like, the maps defined by this thing, either to the left or to the right, as these complementary channels, right? The map to the right is like the direct channel, and the map to the left is the map to the left is the direct channel, and the map to the right is the complementary one. And so it's saying that because in 0 instances, the information ends up here, the complementary channel must basically be completely depolarizing, and the map to the right is this complementary channel, right? So it says that the map to the right, like the map into the system that the referee sees, is one of these depolarizing channels. And then, this always has the form of some state preparation thing, and then you trace out the input, right? That's just the definition of the completely depolarizing channel, and then it looks like this, right? Trace out Q, we have this map from nothing into M. Okay. Okay, so that's that. And then we just need to go the other way. So we need to go from CDQS into F routing, right? So now, again, I won't write it out, but the correctness, so I need to show two things here. I need to show correctness on 1 instances and correctness on 0 instances. Correctness on 1 instances is obvious, right? Because this person is just getting exactly what the referee was getting. And we said the referee can recover Q. And so clearly this person can recover Q, and like the epsilons will be the same. Okay. And then the only other thing we need to show, so let's just say, okay, correctness, epsilon 1 correctness, that's clear. And then we need to show epsilon 0 correctness. And that's following from very similar reasoning. So we're just saying that, so since here on 0 instances, the channel to the right was completely depolarizing, right? The complementary thing needs to be invertible, right? That's what this first statement says, okay? And so we can use that first statement and we can get that, if I purify these systems and I define this map to over here, it's going to be close to the identity. Or there's going to be a channel that inverts it and gets it close to the identity. Okay? So maybe I won't write out the epsilons and stuff, but that's the statement. Okay, so that's how we transform between them. And then we can notice that in the two cases, we used essentially the same resource state. Okay, so it can be a little bit different, right? So when I go from here to here, I can use exactly the same resource state because I'm just tracing stuff out. But when I go back, okay, I had to purify everything here, right, to talk about the complementary channel. And so when I did that, I end up purifying this state. And so when I go back, the state here can be a purification of the state here. So I might have started with randomness here and I have to end up with entanglement over there. But they're going to be very similar in size. Okay, so if I just talk about, the dimension, say, of these systems, they will be, I guess, the same up to a square, or the number of qubits is the same up to a factor of 2. Okay. Okay, so this epsilon 0 correctness also follows, and what we get is that the cost, thought about as the number of qubits in the resource system for CDQS, is within this factor of 2 of the F routing cost for the same function. Okay. And when I go between them, the epsilons and deltas change very slightly by some square roots or 2s, but we're not going to worry about that. Okay. Good. So that puts everything together for us, or that's the last link in the chain that we needed. So we get then, and sorry, actually this one, this is these are basically equal, up to this factor of 2. But for this thing, I only needed one inequality. So we get this thing, we get this statement, up to constant factors. This is true. Okay. So what does that teach us? Well, it teaches us quite a bit, actually. So one thing is that we were studying in an earlier lecture different protocols for doing F routing, right? We had the garden hose protocol and the code routing protocol, upper bounds based on this garden hose complexity or the formula size and other things. Because of this upper bound, we inherit all of the upper bounds that people have proven on CDS, right? So we inherit all these results from the classical literature. And it turns out the classical people have worked pretty hard at this, and they know some surprising things. So for example, they know that the number of random bits that you need to implement CDS for any function is always upper bounded by 2 to the something of order root n log n. Okay. So this is not quite exponential, right? This is sub-exponential. And previously, in the quantum literature, the best upper bound we had for the worst case functions, for generic functions, was exponential. And everybody in the field believed that the worst case would be exponential. or everybody I knew believed that it would be exponential. So this came as a big surprise, when we saw that actually it could be sub-exponential. Another thing that we get is that we get a sort of explanation for why certain problems seem to be hard in F-routing. So in particular, we're going to talk more about lower bounds later, but it's been a big challenge to prove good lower bounds on the entanglement costs in F-routing. Okay, so in particular, the kind of thing that we would like to show, right, but which remains an open problem, is that, some sort of lower bound like this. Okay, so we would like to be able to say that the cost of F-routing is lower bounded polynomially in N for some explicit function f. Like f is the inner product function or something like that, some hard function. We have not been able to prove that. And this is, in hindsight, sort of makes sense that we were stuck on this, because actually the classical people are also stuck on proving polynomial lower bounds on CDS. Okay. And it somehow seems to be quite hard. Putting a polynomial lower bound on CDS is actually, an easier problem than putting a polynomial lower bound on this, because if I get the lower bound here, it would imply one there, right? And already in the classical case, we're stuck. So we get some insight into our difficulties there. If you're an optimist, you can say that we also get like a new approach to proving lower bounds on classical CDS, which is to prove lower bounds on F-routing, right? And we'll talk more about that, hopefully, in a couple lectures. And then, more generally, we just get that CDS is somehow, this establishes CDS is somehow a classical analog of F-routing, and like I was saying, it's always useful in quantum information theory to have classical analogs of the problems you care about, and now we have one, and we can more broadly think about what people know about CDS and if we can carry it over to F-routing. Okay.
It's like you want this to be larger than any polynomial, right? Like
actually, just any polynomial.
Not some polynomial. Like an exponential lower bound.
Yeah, sorry, I should be more clear here. So I would be happy. I would be happy if you proved like omega n to the alpha lower bound just for some alpha. I don't want to say that it's bigger than this for all alpha. I mean, that would be even better, but we're even further from proving that. I want to say, alpha is a half or something, and I can show that there's a lower bound. It seems to be very hard. For classical CDS, the best lower bounds are log n. Unless you're willing to assume that it's either perfectly correct or perfectly secure, in which case you can prove linear lower bounds. But we'd like to get it with like finite errors in the more realistic setting. Yeah. Okay. Okay, so that's it for CDS and the connection between NLQC and classical information theoretic cryptography, at least for now. I want to move on to discuss more general upper bounds on non-local quantum computation. So I asserted a few things in the first lecture, like that for all channels you can do non-local quantum computation, and you can do it with at most exponential entanglement. And I stated some kind of upper bound in terms of the t-depth. So we're going to try and prove both those things. Okay, so yeah, we're going to first of all deal with this generic upper bound that works for everything. Okay, it's based on port teleportation. This is an interesting object in quantum information theory more broadly. So I'll just try and describe this, and then we're going to apply it to non-local computation. Okay, so let's first of all remind ourselves about sort of normal teleportation. Okay, so in regular, we'll call it Bell basis teleportation. You have an entangled state. Each end of the entangled state is the same dimension as the thing you're trying to teleport, right? You make this measurement, the Bell basis measurement. You get some outcome, 2 classical bits per qubit here, right? We'll call it K. And once you do that, we could draw it like this. The state on the other end over here is related to the input state by some Pauli, pk, which is fixed by the measurement outcome, right? Okay, so port teleportation. Well, okay, so let me say there's a couple of key ingredients here, right? We have this entanglement, we have a measurement, and we have a correction operation, which is here the Pauli. Okay. So port teleportation has the same ingredients, but they're all kind of changed. Okay. There's a measurement. It's no longer a Bell basis measurement, it's something more complicated. There's entanglement, but it's now a larger state. Okay, so before this had the same dimension as this. Now each of these wires has the same dimension as the input. Okay, but there's a whole bunch of wires. Okay, there's we're going to call it big N wires. Okay, the different wires we're going to give the name ports. Okay. So there's N of them, right? So there's these N ports. And after you make the measurement, the following thing happens, like the analog of that equality, which is that most of the ports end up in some state that we don't care about. Let's call it, big psi or something. But one of the ports ends up approximately in the state that I put in. Okay, so if I put in psi here, these N ports, almost all of them turn into junk, except for one of them, which turns into approximately the input state. Okay. The measurement outcome here, I, labels which port turns into the input state. Okay. So now, again, there's some correction operation I can do to get back the input, or approximately the input. But the correction is different now, right? The correction is you should trace, let's call these ports B, B1, dot, 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 Bn. You should trace over all but the ith port, right? Whereas here, the correction is to do pk dagger, which is the same thing. Okay. Okay, so it's kind of surprising that exists. In the notes, I go through and describe this in more detail. So describe what this measurement is, why it works, give some intuition for why it works. I'm going to skip that here. And we're just going to put this to work. I'm going to put this to use in the in the non-local quantum computation context. Actually, let me say one more thing about this. How close is this approximation? Okay. This is epsilon. Oh, okay. So this is not exact, right? So I should quantify how close we are to being exact. And at least the most naive version of this is this close. Okay. Tau is the channel defined by this whole procedure, right? Like stick in the state, make the measurement, trace out all the junk, right? So that's a map from the input system back to the input system. And it's this close in diamond norm to being the identity. So it's 4dA squared over the root of n close. Okay, so you can see that you have to take the number of ports here to be exponential in the number of qubits that you put in. Okay, and it's like, you know, here it's something like 2 to the 4 NA because of the root and the square. You can improve this exponent. There's a bunch of recent work optimizing port teleportation, but even the optimized versions are still exponential. It's just this is smaller. Okay, and we're just going to deal with this simple case. Or that's the simplest one to understand.
Sorry, maybe one question. Is the measurement independent of psi?
Yes. Yeah. So it's teleporting an unknown quantum state. Okay. So yeah. So how do we use this in NLQC? Okay, so there's going to be a few steps here. So we're trying to do, right, we're just trying to do an arbitrary arbitrary channel as a NLQC, okay? And okay, there's a few steps. Step one, we're going to use a regular teleportation to collect the A and B systems together. Okay, so like Alice has A, Bob has B, and we're going to start out by using an entangled state with the same dimension as A. We're going to do a regular Bell basis teleportation. Okay, so that now A is over on Bob's side, but it has this poly acting on it, right? And I'm going to, for convenience, maybe I'll use another color. I'm going to start drawing this like combined, like sort of A dimension wire and B as a single blue wire. Okay. Okay, so that's the first thing I do. So the first thing we do is like, we do a regular teleportation, or at least the measurement from a teleportation, right? We haven't communicated anything yet. Everything's instantaneous. Okay, and then what we're going to do is we're going to send the blue wire back to Alice, but we're going to port teleport it back. Okay, so now we have this initial measurement. We have the blue wire. We're going to do the port teleportation measurement. Okay. So there's n of these. And so now, like, what does Alice have? She knows the measurement outcome from here. She knows K. Okay. Bob, meanwhile, knows I, the measurement outcome from there. And Alice holds these n ports, right? On one of which there's almost the whole input state, right? So like she has AB on one of those ports, but it's messed up by the poly, right? She knows which poly it is, but she doesn't know which port the state is on. Okay, so what does she do? She just acts on all of them with the needed poly. Okay. So okay, let me draw this one more time. Okay, so we teleport it back. Right? Okay, so Alice is going to do PK like on the B part or on the A part. On all of the ports. So most of those were somehow not really necessary, right? They're acting on what's going to be the junk, or what is the junk. But she doesn't know which is the junk. She just does it everywhere. Okay, and so now what does she have? Well, she has the full state, like the AB state, on one of the ports, but she doesn't know which one, right? So what should she do now? Well, she should just do the channel that they wanted to do, but to all of the ports, right? Because she doesn't know where it's supposed to happen. So they do N everywhere, right? And then finally, this blue wire, right, consisted of like two little wires, the A prime, or the A and B part, which are now A prime and B prime, right? And so she takes A prime, there's a whole bunch of them, she doesn't know which one's the correct one, but she knows that the correct one has to end up on the left, right? So she keeps all of the A prime systems, like the A prime 1 and all the way to the A prime n. And then for B, she knows that, she doesn't know which is the correct one, but she knows that the correct one needs to go right, so she sends all of the B's over to the right, right? Okay, so I should have drawn this a little bit lower. Okay. Over on the right, Bob has this outcome I, right, that says which port is the correct one. So he's going to take that and he's just going to send it to both players. He's going to keep a copy and he's going to send a copy over to Alice. And then at the end, they just trace out, everything except the correct port. This is AI bar. Traces out BI bar. Okay, and then what they're left with will be the correct subsystems which have the channel done to them. Okay. Okay, so that's the whole thing. And then how much entanglement did it use? Well, the dominant cost came from the port teleportation, right? There is also this thing, but that was a linear cost. That was just the size of the same size as the entanglement is the same number of qubits as there is in A, right? It's linear. And so the entanglement cost is dominated by these things. And so it's like n times 2 to the 4n, over epsilon squared. And that just comes from thinking about if I want to achieve some accuracy epsilon, how big do I take n here in terms of A? Okay. Okay. So yeah, an important open problem here is we don't know if this exponential scaling is intrinsic, like if you can do better for a generic channel than the exponential cost. You can lower this exponent a little bit by optimizing the port teleportation, but yeah, we don't know if it can go sub-exponential. I think it's unlikely, but the fact that in the CDS context, that was some big class of non-local computations that did turn out to have a sub-exponential cost in all cases, it's at least vaguely possible that there is some sub-exponential scaling here, or that you can do better. Yeah, and it's open to prove that, for a random channel or a random unitary, or somehow a generic or worst case one, that there's actually an exponential cost. We do know that the cost of port teleportation itself has to be exponential. We can lower bound that, but we don't know if in the overall protocol you maybe had to do something like port teleportation and then that imposed an exponential cost, or yeah. Okay. Okay, so we've seen that, in some cases, like F routing or F routing with a very structured function F, you can, go much lower than the exponential cost. The next thing we want to understand is can we make some more general statement about a unitary, its structure that lets you reduce the entanglement cost? What are examples of easy unitaries that can be done with, say, polynomial entanglement? And that leads us to this other upper bound I mentioned, which is based on the T depth. Okay. So somehow it turns out that if you don't have too many T gates, if you're not too magic, then it's easy in this context. So the simplest starting point there is to just think about Clifford unitaries. Okay. And I claim that for a Clifford, or maybe I should say, so recall that for a Clifford, C, a unitary, is said to be a Clifford if C, P, C dagger is a poly Okay, so for all strings of polys on n qubits, if I conjugate it with this operator C, I get a poly again. That's the defining property of a Clifford. It turns out that being a Clifford makes it really easy to implement as a non-local computation. So why is that? Here's a simple protocol. I take my input A. I just do a regular Bell basis teleportation, right? I have my system over on the right. Now I just go ahead and I do the Clifford, right? I just do C. Okay. And then I send this A part back and I keep this part. And then I take K, the classical outcome, and I send it to both sides. Okay, and then I claim that you can sort of fix things up and implement the overall Clifford here. So why is that? Well, it's fairly simple to see. So this measurement, what it does, right, is puts this state over here with some poly acting on it. So at this point I have PK B. So if I just do the Clifford, I use this property that the Clifford conjugates polys to polys. to note that that is the same as first doing the Clifford and then doing some other string of polys defined by the conjugation of P with C, right? Okay, so now here, the state here is like the correct one with these polys messing it up, right? So I wanted C acting on psi, and I have almost that. I have Q twiddle acting on C psi. And so what do I do at the end? Well, I just undo the Q's, right? Using the fact that I know K now because I've communicated. Okay. So what's the entanglement cost here for a Clifford? It's just at most linear, right? In particular, the only entanglement I used was to teleport this thing over there. And so this just needed to be as large as this input. Okay. Okay. Okay, so we kind of want to keep going from here. So we know that Cliffords are easy, they're linear. In the worst case, we might get up to exponential, but can we do something in between? Like if I add a couple of T gates, can I keep the cost low? Okay, and okay, that's what we're going to show. So the claim is that the entanglement cost for unitary will be upper bounded by some constant times n, we call it like kappa, to the T depth of the unitary. Okay? Where the T depth means, so remember that a T gate, this is 1 e to the I pi over 4. Okay, and this is not a Clifford, right? And the Cliffords plus this thing form a universal gate set, so you can build anything out of T plus Clifford. Yeah, okay, and then by the T depth, we mean we're going to think of the unitary as written as like, 1 Clifford, and then a layer where you can have as many T gates as you want, but all in parallel. Not necessarily everywhere, but as many as you want, up to n of them. And then C2, and you just keep going like this until there's some final Clifford, CD. Okay. And the number of alternating layers here, Clifford T, that I need is the T depth. Okay. Okay. So we're going to try and show this upper bound. It's pretty complicated. It'll probably take me through to the end of next lecture. And so it's a little involved. Please ask questions. Keep your wits about you. So to get there, we're going to have to actually go back to this garden hose model. We're going to need some tricks from the garden hose to do this. So I got to show you a couple things about that. The first is that there's this sort of standard form for a garden hose protocol. Okay. Okay, so how does this work? An arbitrary garden hose protocol has this like tap as an input, right, where the water comes in. And then its defining property is that, if F is 0, the water is going to spill on the left somewhere. And if F is 1, the water is going to spill on the right somewhere. Right? But there could be multiple different places. Like, depending on the inputs, the water could spill, like, I have multiple different 0 inputs. The water could spill out of multiple different pipes on the left. That's fine from the initial definition of the garden hose. We're going to modify it to say that there's just going to be 2 possible spilling pipes. It's always going to be here if F is 0, or it's always going to be here if F is 1. One particular pipe. Okay, and then the claim is that I can make that transformation without too much overhead. Like the cost here is not that different from the cost there. Okay, so why is that? We can see the following construction. So let's start with an arbitrary garden hose for the function f, garden hose protocol. I have my tap. I can have multiple spilling pipes on the left and on the right. Let's just say 2 of them. Okay. I'm going to make a copy of the protocol. And another copy. Okay. And I'm going to do the following thing. I'm going to take the possible spilling pipes here, and I'm going to connect them to their partners, to their corresponding pipes up here. Okay, so the 0 ones on the left, I connect to this copy. And the 1 pipes on the right here, I connect to this copy. Okay. There's the 2 pipes that serve the role of the tap in these protocols. Those now become the 2 possible spilling pipes. This one is the 0 spilling pipes, and this one is the 1 spilling pipes. Okay. So why does that work? Let's just look at an example, and it'll probably become clearer. So here's my initial garden hose protocol. Let's say there's 2 pipes, okay? This one's connected to the tap. And then, condition on X and Y, I make some set of connections in my protocol. Let's say that for this particular X and Y, I connected this one and this one. Okay. Actually, maybe I should make this slightly more interesting. So let's add a 3rd pipe like this. Okay, so I have these 3 pipes. I run another copy of the protocol, so the same things get connected. That gets connected. And then I take the open pipes on the left, and I connect them to the open pipes on the left here, right? So this goes to here. This goes to here. And then I take the open pipes on the right, and I connect them to the open pipes on the right over here. And then let's look at what happens. So the water comes in. In the initial protocol, it was going to spill on the left, right? So this was like a 0 instance. So the water came out one of these, in particular into this one, and then it ran through here and back out the tap, right? And in particular, what's happening is that because this is connected up the same way as this, when I feed like the output here into the like what was the output here, it was running forward through some path here. It will now run backwards along the same path here. And so it will necessarily come out where it went in here, which is the tap. Right? So the fact that it spilled on the left here now means that it comes out on the left on this tap. Right? Similarly, over here, I've connected, this to here. Now, the water was not spilling out from any pipe on the right. So we know that the water is never going to get into the system on the right, and it's never going to come out of the tap here. Right? And then, if the things have been connected up a little bit differently, such that this was a 1 instance, maybe in a 1 instance, this gets connected as well. Now that's connected. Now it comes in here and it runs through it backwards and it comes out there. Right? Okay. Okay, so what this is saying is that like the garden hose cost in the standard form is never more than 3 times the garden hose cost in the previous form. Okay? Okay, so that's one like neat property of the garden hose model. Oh, okay, I guess I'm out of time, so I will next time show you one more property of the garden hose protocol that we'll need, which looks like this. So it's called the XOR lemma, and what's this? Okay, so it's saying that if I have a function here that's built out of XORing a bunch of smaller functions, that the garden hose cost for that thing is basically the sum of the garden hose cost for the individual things up to some factor of 4. Okay. If you want a fun puzzle to think about, try and connect hoses up in such a way that you can do this. Okay, we'll leave it there for now. Thanks.